Good afternoon, everyone. Today, I will continue with the introduction to organic chemistry. I have done another video on the shapes of molecule for organic molecules, focusing on sigma and pi bond and about hybridization. So that is done in another video. You can check out my YouTube channel for the video. Today, I will be focusing on the introduction to organic chemistry, on the different functional groups of organic compounds, the reactivity, some of the terms that you should use, and focus mainly on isomerism. All right. So basically, when we talk about organic chemistry, we are focused on the element carbon. Okay. So organic chemistry is the chemistry of compounds of carbon and hydrogen, with the exception of carbon monoxide, CO2, CS2, and other various bicarbonate, carbonate, and cyanide, which are considered inorganic. We shall not deal with them in this topic. In the past, when we use the term organic, it refers to compounds found in living plants and animals. But we can actually make organic compounds in the lab without extracting them from living organisms. There are three important properties of carbon. Number one, it consists of carbon which has a fully shared octet of electrons in its compound. So when carbon forms compound, by sharing electrons, it will obtain octet configuration. And carbon can form strong single, double, or triple bonds. Carbon forms 4 covalent bonds, so expect a chain of carbon atoms with different groups attached to it to lead to a wide diversity of compounds. They are stable because there's a lack of lone pair of electrons in the skeleton chains, and the inability of carbon to expand its valence shell to accommodate more than 8 electrons. It has only 2 covalent shells, by the way, and presence of strong carbon-carbon and carbon-hydrogen bonds. The oxidation number of atoms in element is always 0, but in a compound, the more electronegative atom will be given a negative oxidation number. However, the sum of all the oxidation number in the molecule will still be 0. Now, these are some examples of common oxidation number of the element we are familiar with. Oxygen -2, acid peroxide. Hydrogen is +1 or -1. Fluorine is always -1 because it's the most electronegative element. Now, bonding electrons are assigned to the more electronegative atom. Okay, that's logical. Thus, for every bond, the more electronegative atom gains an electron, and oxidation state will decrease by -1. The less electronegative atom will lose that electron, and the oxidation state will increase by +1. If the bond is formed between 2 atoms of the same element, no net gain or loss of the electrons. Carbon is actually less electronegative compared to fluorine, oxygen, nitrogen, chlorine, bromine, iodine, and even sulfur, and is more electronegative than hydrogen. So this is the list in order of electronegativity from the most to the least electronegative. This method is useful for any compound when an element occurs multiple times and might have different oxidation state. Let's try this exercise. What is the oxidation number of carbon? So surrounding the central carbon, you have 4 hydrogen, and hydrogen will be +1, +1, +1, +1. So in order to balance that, carbon will be -4. In tetrachloromethane, we have fluorine being the more electronegative atom. So you have -1, -1, -1, -1. Then carbon have no choice but to become +4. So carbon is quite flexible. It depends on the compound it is in. How about this one? Okay, for this one, chlorine, -1, -1, hydrogen +1, +1. So overall, 0, carbon, 0. Now, to calculate oxidation number of carbon in methanol, methanol, and methanoic acid, how do we do it? Now, and state the type of reaction undergo when methanol is converted to methanol and methanoic acid. I think we learned that before, is oxidation. But let's count the oxidation number. So for carbon here, the oxygen will be -2. Okay, oxygen is -2. +1, +1, +1, +1. So you just focus on what is surrounding carbon, the immediate neighbor. So carbon is +1, +1, +1, here -2. So you have plus 1. So overall, you have plus 1, plus 1, plus 1, plus 1. Then you have plus 4. Okay. Okay. The immediate neighbor, okay, let's look at the oxygen first. The oxygen is a bit tricky because it's bonded to both C and H. So the hydrogen here is plus 1. Okay. Oxygen by right, if let's say only with another element is -2 by itself, like MgO. But in this case, right, it really depends. So plus 1 here. So this oxygen here, right, this whole thing, it starts -2, but this whole thing, right, will become -2 plus 1 minus 1. This whole thing. So the one next to carbon is -1. Hydrogen here, plus 1, plus 1, plus 1. So to balance the -1 plus 3, -2 plus 1 minus 1, -2. Overall must be 0, right? So 3, 4, 4 minus 2. Yeah, look at it in this way. So here is plus 1, plus 1, plus 1, plus 1. Okay, this is -2. So you have plus 4. It should be -2. So plus 2, 0. Should be -2. So this is wrong. Yeah. So this one should be -2 to balance the whole thing. Yeah, that's why I find it very, very puzzling. So this is -2 plus 1. So overall here will become -1. So 3 minus plus 3. So here plus, so this one plus 3, so minus 1 to balance the plus 3, you must put a -2 here. So it's -2. So the answer is wrong. Here, -2 for oxygen alone. Okay. Then here become -1 because it's affected by this H. So it become -1, the whole thing here. Here -2, here +1, +1, +2 -2, 0. How about the methanoic acid? This one is -2, but become like that, -1, -2, +1. So to balance, you have to put a +2. Okay? So -2, 0 to +2. Determine the oxidation number of all the carbon atoms in the following compounds. Okay? So for this one, let's look at it one by one. The carbon here on the left-hand side, okay, here to here, you consider 0 because same atom. Then here, you put +1, +1, +1. So this one will be A. To be -3. Then this one, +1, +1, -2. Ayo. This one, +1, -2, but here -1, -1, +1, +1, +1, +2, 2 plus 2 plus -1. This is correct. So it's -3, -2, -1. Okay. This one +3. This one also -3. This one is -1, +1. Okay, +1, -1, yes, 0. Okay, and this is so it should be -3 as well. Okay, Wrong. This one is -3. This one is -2. Oh my God. Okay, this one is -1, -2. Then you have zero, -2, -1, +3. Okay. Okay, next, bonding and shapes of organic molecules. So we talked about that in the previous chapter already on chemical bonding through hybridization and resonance. So the importance of hybridization is that it explains the shape of molecules, the bond angle, and the bond length in molecules. So carbon typically shows 3 types of hybridization: sp3, sp2, and sp. And sp3, the shape of molecule will be tetrahedral. sp2 will be trigonal planar, and sp will be linear. All right. Now, list the hybridization state of each carbon atoms in the compound. So we have one here. So you have double bond here. So it will be sp2, this is sp3. This is also sp3 tetrahedral, this is sp. Then for this one will be sp2. This one will be sp2, sp3. Just this three. This one also get sp2. Okay. Now, how organic compounds are classified? Based on the arrangement of carbon skeletal. So they can be aliphatic hydrocarbons, alicyclic, or aromatic. For aliphatic hydrocarbons, they are open chains of carbon atoms containing single or multiple CC bonds. So they can be straight chain or branch chain. They can be saturated or unsaturated. For alicyclic, they contain rings that are closed of carbon atoms. It can be either single or multiple bonds. The hydrogen atoms are typically not shown in the structure. For example, like this, you don't show the hydrogen and you don't label the C. Okay, so each line represents 2 carbon atoms bonded together. This is called cyclobutane. The hydrogens are not typically shown like this. No, that's not correct. This is the skeletal formula. Skeletal formula, yes. The aromatic one, we will elaborate in the topic of benzene. Now, since organic compounds may also contain elements other than H and C, a more effective way of classifying them will be on the basis of functional group and homologous series. A functional group is made up of an atom or group of atoms within the organic compound responsible for characteristics, chemical properties. A homologous series is a family of compounds having the same functional group. Homologens refers to members in the same homologous series, and they have these properties represented by the general formula, differ from the successive member by a methyl or a CH2 group. Gradual change in physical properties like boiling point because of different molecular mass. Similar chemical properties due to the similar number of valence electrons or number of electrons they may have. Can be prepared by similar methods. So for example, in alkane, these are the first 4 members. And these are the functional group presence for the different homologous series. Alkane, there is no functional group. Alkene is the CC double bond. Alkyne, CC triple bond. Halogen derivative, the halogenal alkane, which are known as the group 17. Okay, they consist of hydrocarbon with a halogen bonded to it. Halogenal arene refers to the benzene ring with the halogen bonded to it, replacing one of the hydrogen atoms. For hydroxyl compounds, we have alcohol, phenol. Carbonyl compounds, we have aldehyde and ketone, where the carbon is attached to the hydrogen atom for the aldehyde. As for ketone, no hydrogen atoms bonded to the carbon, that is bonded to the O. As well as carboxylic acid, which you should be familiar with, ester, and ethyl halide, which means this X is not OH, is replaced by Cl or Br, a halogen. And this will be the last topic in organic chem where we'll cover later. Nitrogen compounds, we have amine, amide, amino acids, and nitrile. Now, so to identify the various functional group, this is how we do it. Okay, I just show you. You can refer to the table above for reference. Now, organic compounds are represented by either empirical formula, molecular formula, or structural formula. For structural formula, we have the condensed or structural formula, displayed formula showing the full structural formula, stereochemical, and skeletal. For empirical formula, you are supposed to be very familiar with. It shows the simplest ratio of the different types of atoms in the molecule. Molecular formula shows the actual number of each type of atom in the molecule. As for the structural formula, condensed structure, it only shows how the group of atoms are sequentially arranged. For full structural formula or displayed, it shows how every atom in the molecule is bonded to other atoms and the number of bonds between them. The C and H in rings are not shown. In stereochemical, we show the spatial three-dimensional structure of the molecule. Solid line represent bonds on the same plane as the paper. Dashed line represent bonds receding into the paper, and the heavy wedge line represents bonds coming out of the paper. So this is a 3D representation. And this and this. Skeleton formula shows the carbon skeleton with any functional group such as OH or Br. The straight line represents the CC bonds, and we don't show the C and H atoms. How to draw skeleton structure? Now, carbon atoms in a straight chain are drawn in a zigzag manner. The end of each line represents a carbon atom. Double bonds are shown with 2 lines, triple bonds, 3 lines. The direction in which single bonds are drawn is irrelevant. Hydrogen atoms cannot be shown. The number of hydrogen atoms may be inferred by the fact that each carbon atom forms 4 bonds. Heteroatoms are drawn, and any hydrogen atoms attached to heteroatom will be drawn. So you can convert this to this. And make sure they are drawn in a zigzag manner, because it is the shape is tetrahedral. sp3 hybridization. All right. More examples for reference. And more. And more. You see, for OH and NH2, you have to write it down. Okay, this is only for C and H. The one that you don't have to write is C and H, but the rest of the heteroatom, not C and H, you must represent it in the skeleton formula. When drawing the structure of the molecule, ensure that the structure drawn is not ambiguous, like this one. No. Acceptable, 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 not acceptable. Acceptable, not acceptable. This is not acceptable, will not be given the mark. You have to show the arrangement the sequential order. Nomenclature. The most common way to name organic compounds is to use the systematic naming developed by IUPAC. So each name consists of a root, a suffix, and a prefix. Now, the prefix represents the substituent or the side groups. The root denotes the longest continuous carbon chain bearing the principal functional group. And the suffix denotes principal functional group. Like this. So 2-bromo-pentanoic acid. So the 2 refers to the position of the bromo is bonded to the second carbon. The longest continuous carbon chain will tell you how many carbon atoms in that chain. And the principal functional group will tell you the main functional group. Now, in the aliphatic straight chain system, the mean of the root takes its name according to the number of carbon atoms in the longest continuous chain, like this. For the saturated hydrocarbon, the mean of the root ends with AN. For unsaturated hydrocarbon, the mean of the root ends with EN. Unsaturated hydrocarbon with C triple bond C bond, the mean of the root ends with YN. So these are the 10 carbon atoms that you need to remember: meth, eth, pro, bute, pen, hex, het, oct, non, den. Okay. There is a mnemonics here, but up to you to remember. You can say, Mary eat peanut butter. Peter hates having oranges and durians, something like that. Now, for unsaturated hydrocarbon with C double bond C, the position of the double bond is denoted by the lowest carbon number possible. So instead of it can be either, so you need to be very clear for alkene, right? Is it build 1 in or build 2 in? Okay. Okay, let's continue with where we stopped. Okay. Now, for saturated hydrocarbon, the name of the root ends with AN. For unsaturated, the ring of the root ends with EN. Unsaturated hydrocarbon with triple bond, YN. So for unsaturated hydrocarbon with C double bond, the position of double bond is denoted by the lowest carbon number possible. So this one, although it's on the right side, you still call it 1 and not 4. This one is in the middle, 2. In alicyclic system, the word cyclo is added to the front of the root corresponding to the same number of carbon atoms. So this is 5 carbon atoms, cyclopentane, 6 cyclohexene. Now, the suffix. It indicates what functional group is joined to the chain. So if you have this, it's called carboxylic acid. Ester, acid halide, amide, nitrile, aldehyde, ketone, alcohol, and amine. When there's more than one functional group in the compound, the functional group placed higher in the table is listed as a suffix, with everything else being a prefix. So let's say you have this compound. So this is actually, 3-amino-butanol. CHO is found higher in the table. So this is the reference. This priority. The highest is the acid, followed by ester, and the last one is amine. So obviously the amine is lower than CHO. So the sulfate is Al, and NH2 is becoming the prefix amino. All right. As for this one, the acid COH, carboxylic acid, is found higher in the table than CHO, the aldehyde. Correct. So the sulfate is OIC acid and CHO is a prefix. So we call it OXO, oxo. So we call it 4-oxo butanoic acid. These are uncommon ones. So prefix wise, right, these are the name. So denotes all the functional group on the root. So nitrile, C triple bond N is cyno. Aldehyde ketone, oxo. Alcohol hydroxyl. This is called amine, amino. Ester, alkoxy. halogen, bromo, chloro, chloro, and iodo. This one is called nitro. Then we have phenol, alkyne, methyl, ethyl, propyl. So this is the whole list that they will be testing you on. Arabic numerals are used in the name to indicate the position of the attachments of the substituent, multiple C to C bonds or principal functional group. These numbers are called positional number. So these are the steps to take to name compounds. Now, number one, identify the principal functional group and then select the longest continuous carbon chain containing the principal functional group and count the number of C atoms. So the principal functional group here is this, because this is of the highest priority. So it's OH acid. The number of C in the parent chain will be 7. Okay, so it's called heptal. The prefix, we still have a few. We have CH3, NH2, and Cl. So we name them as methyl, amino, and chloro. Next, number the C atoms in the main chain from one end such that the lowest number is given to the group cited as a suffix. Then the lowest possible individual number to groups cited as prefix. So for example, for the position of the principal functional group will always be 1. It must be the first carbon. And then the position of the amino function will become 3. Because this is 1, so you follow. Chloro is 2, nitro is 3, and the 3 methyl substituent will be 4 and 5 respectively. Now, next one, you string the prefix together. If the same substituent appear more than once, indicate using di, tri, tetra, etc. The appropriate position number is still required if the groups are connected to the same carbon on the main chain. Different prefixes are listed in alphabetical order. Multiplying prefixes does not apply to the alphabetical order. Commas are used to separate numbers and hyphens to separate numbers and words. So this one will be called alphabetical order first. So A comes first. So although amino is in the third one, you still put it first. So 3 amino, chloro come before the word methyl. So don't care about the trial. So it's 2 chloro, but because there are 3 methyl, so it's 4,4,5 trial methyl. And lastly, right, you string the last part, the IUPAC nomenclature for compound A. Which is the heptanoic acid, because there are one longer chain is here, so there are 7. So heptanoic acid. And these are the exercise where you can make reference to. Now, let's go on to the terminology with organic reactions. So, mechanism. Organic reactions involve breaking and forming covalent bonds. Every reaction involves the flow of electron density from electron rich to electron poor. So electron move to break bonds and form new bonds. So the mechanism illustrates how electrons move during a reaction. A curved arrow are used to show the actual movement of electrons. The tail shows where the electrons are coming from, either from bond pair or lone pair. The head shows where the electrons are going. And mechanisms are proposed to be consistent with the reaction stoichiometry, the rate equation, and all available experimental data. There are 2 types in which covalent bond can break. First one, homolytic fission. So in the breaking of covalent bonds such that 1 electron goes to each atom, they form 3 radicals like this. So you represent in this way, and you show a half arrow to show the movement of 1 electron. If it's heterotic fission, meaning the breaking of covalent bond goes to such that both electrons go to the same atom, and it forms positive and negative ions as a result. So this is a full arrow to show movement of a pair of electrons. There are 2 ways how this can occur. Like you can have both electrons go to the leaving group. This occurs when the carbon is less electronegative. The positively charged carbon ion is called carbocation. Okay? Or you can have both electrons go to carbon. This occurs when carbon is in fact more electronegative, and the negatively charged carbon is called carbon anion, carbocation. The degree of substitution of an atom in an organic compound is determined by the number of alkyl or aryl groups bonded to it. So the organic compounds with different degrees of substitution may undergo different reactions. So we have the primary, secondary, and tertiary. So let's say you have one R group bonded to the carbon bearing the OH. We call it primary. 2, secondary. 3, tertiary. So that's how we classified it to show the degree of substitution. Likewise, we can apply that to carboxyl ion. Primary carboxyl ion, we have one R group bearing the positive charge carbon. Secondary and tertiary. We can also apply to amine, primary, secondary, tertiary, because amine can hold up to 4 bonds if you have, so it can be quaternary. Now, let's introduce you the type of organic species. Like we have electrophile, it's an electron pair acceptor, which is also a Lewis acid. All right. So electrophile are electron deficient. Okay. They are attracted to regions of negative charge of regions of electron-rich sites. And they may possess an empty orbital to accept the electron pair. Nucleophile is the opposite. It's the electron pair donor and is also a Lewis base. It's electron-rich species. They are attracted to regions of positive charge or regions of electron-deficient sites. They possess at least one lone pair of electrons. Free radical contain unpaired electrons from the homolytic fission of covalent bond, and they are electrically neutral. Let's go through the types of organic reactions you will encounter in the syllabus. Like addition occurs when there is unsaturation in the molecules, when two substances react to give a single product, and the pi bond is broken to form two sigma bonds, and the sigma bond remain unbroken. Like electrophilic addition, alkenes, you have this. The pi bond is broken to form two sigma bonds. Nucleophilic addition is another example. You break the pi bond to become sigma bond. Substitution, where one atom or group of atoms is replaced by another atom or a group of atoms. Two substances react to give two products. All right, like this one, free radical substitution in alkanes, and electrophilic substitution, and nucleophilic substitution. All right, so this is just a preview of what is going to come. Elimination involves removal of atoms or group of atoms from adjacent carbon atoms to form multiple bonds. So it's like forming back the double bond. It's the opposite of just now when you break the double bond. Hydrolysis involves water breaking the bond in the molecule. Okay. So this R kick out, replaced by the H. Or condensation, where two molecules react together to form a bigger molecule and eliminate smaller molecules such as water or even HCl at times. So this one break, form with which one? The O and the H2 come out to form H2O. Oxidation, as shown, you are very familiar with it. Reduction and rearrangement, where there's a migration of a group of atoms from one side to another. Okay, some terminology related to organic reactivity, starting with delocalization. Just as two p orbitals can overlap sideways to form a pi bond, two or more pi bond can overlap with each other to form a more extensive pi bond. For example, benzene, C6H6 is a planar 6-member ring of sp2 hybridized carbon atoms. The unhybridized p orbitals of the carbon atom could overlap to produce 3 CC bonds between atoms 1, 2, 3, and 4, 5, and 6. So the overlap to produce double bond between atoms 2, 3, 4, 5, and 6 and one of the ring is just as likely to occur. So it means that all the 6 p orbitals actually can overlap with each other to produce a set of 6 delocalized pi electrons. These These 6 electrons, right, are said to participate in resonance. Okay, and they happen to find out that these all 6 CC bonds have the same bond energy and bond same length. Same. and it's somewhere in between these. So it's a transition between them. So electrons can move freely lah, like this. Move freely in the ring lah. An atom of a group of atoms is said to be electron withdrawing substituent if it decreases the electron density in the compound. It is said to be electron donating substituent if it increases the electron density in the compound. Such electronic effect is either due to donation or withdrawal of electrons through the sigma bond due to electronegativity difference, or delocalization of the lone pair of electrons on the atom adjacent to the benzene ring into the pi electron cloud of the benzene, or delocalization of pi electron cloud of benzene onto the substituent. So there are some examples of such substituents in benzene, like this one. O is more electronegative, so O is withdrawing electrons. And you have another one here. And also for electron donating, right? So this NOO and this COH, they are actually withdrawing the electrons away from the benzene. But for these two, right, they are contributing electrons, so they are electron donating. Steric effect or steric hindrance, which actually prevent reaction. Steric hindrance occurs when the presence of the substituent hinders the approach of the attacking reactant and prevent reaction to take place, or lower the reactivity of that particular site within the molecule. So for example, this one, these two compounds, right, look quite similar, but they are not the same. They undergo very different mechanism when reacting with OH minus. All right, this is known as the nucleophilic substitution. So this OH is nucleophile and is attacking the positive carbon center. Okay, in this case. However, when you have so much bulky groups, right, surrounding the central carbon, CH3 is larger, and CH3 will hinder the nucleophilic attack of C by the OH minus. So the reaction will proceed by a different mechanism due to the steric hindrance available. The three methyl groups hinder the approach of nucleophile towards the electron deficient carbon. Now, let's talk about the big concept here, isomerism. Isomerism refers to existence of two or more compounds that have the same molecular formula but different arrangement of atoms in the molecules. So they are known as isomers. And we can classify them under constitutional and stereoisomerism. Some of it are learned at O level already, like the structural isomerism. So constitutional or structural isomerism, the isomers have the same molecular formula, but different structural formula, which is the different arrangement of atoms. We can further classify that into chain isomer, where it differs in the arrangement of carbon atoms, one straight, one branch. And they will definitely have different physical properties, but chemical properties similar due to the same functional group. As for positional isomers, right, they will be the same homology series, but the functional group is located at different positions like this. Okay. As for functional group isomers, the functional groups are different physical, different chemical properties like ether and alcohol, aldehyde and ketone, carboxylic acid and ester, alkene and cycloalkane. Now, how do you draw the constitutional isomers of the organic compounds with the molecular formula C4H10O? So these are the systematic way of drawing it. Number one, identify what is the main functional group. So is it alcohol or is it ether? Okay, so it can be either or. For one functional group, identify the longest chain and draw all the possible positional isomers. Branch the chain and draw all. So you branch out and then you draw all positional isomers, and you repeat step 2 and 3 to find for the other functional group. So it can be either alcohol or ether. So for alcohol, it can be here, here, or like that. You branch out one of it. Yeah, you branch out the chain. You branch another one more time again. Ether, move the O at different position, or branch out one of them. So there are 7 isomers. Now, stereoisomerisms, right, refers to the existence of two or more compounds that have the same molecular formula and structural formula, but different spatial arrangement of atoms. So we have the cis-trans and the N-enantiomerism. For cis-trans isomerism, right, these are the conditions to be met. Number one, there should be restricted rotation about a bond, either by the presence of double bond or the ring structure. For the alkene, each carbon atom in double bond must have two different groups attached to it. For the cyclic compound, two or more of the carbon atoms in the ring have two different groups attached to them. So for the alkene, right, the CC double bond cannot undergo free rotation unless one of the bonds is broken. So the CC double bond will restrict rotation, and therefore we have this. If each of the carbon in CC bond has two different groups attached, two stereoisomers are possible. One, we could have a cis isomer where there are two identical groups on the same side of the double bond. We have the trans isomer where two identical groups are on the opposite side. So J and K, right, in this case, right, are identical. They are not even cis-trans isomerism. Yeah, because it's bonded to the same carbon, it must be different carbon. The B and D must be different carbon. Yeah, because one of the C atoms is bonded to two identical groups, so cannot. It must be the identical groups, right, must be bonded to two different carbons. Yeah. So cis-trans isomers have similar but not the same chemical properties. So they react the same reagent, although at different rate. But for physical properties will be very different. So let's look at it. It's quite unique. Why there is a discrepancy? Like how come like cis isomers, right, the melting point is lower, but the boiling point is higher than the trans. So compared to the trans isomer, the cis butene, right, has a higher boiling point because it is more polar. It has a higher polarity. So there's a slight net dipole moment compared to the trans. Lower boiling melting point is because, right, it fits into a crystalline lattice more poorly. Yeah. If you have identical groups on the same side, it's very difficult to pack in a container, in the whole structure. Now, if the number of such CC bond in a compound is n, the maximum number of cis-trans isomer will be 2 to the power of n. Okay. Exercise 7. Okay. This answer is all given. Okay, take a look at this question. Yeah. First. Okay, for this question, you're supposed to state the number of cis-trans isomer for penta 1,3-diene because there are two double bonds of C and one bromo penta 1,3-diene. So start with the first one here. Number of CC bonds will be 1, 2. Cis-trans will be 2 to the power of 1. Because there are two double bonds, so it's 4 possible isomers of cis-trans. So this one is, it's not even drawn properly. Cannot draw like that lah. So this one is the 4 isomers is like this. Okay, cis 1 bromo penta 1,3-diene. Cis-trans 1 bromo penta 1,3-diene. So this one, 8. This one on the same side. Then this one, cis, then cis, then cis, this one is the opposite of this trans. Yeah, 1 bromo penta 1,3-diene. Then this is trans, but here cis. Here trans again. Then this one there. This one got 2 possible isomer only, right? So one of it could be this one cannot be here, it's here. So it is Okay. Will be this. Probably this one, here. They're all in the same plane. Okay. CH. This is correct. Yes. Okay. So this one is cis because these two larger group is on the same side. So cis enter 1,3 diene. And the other one, just shift one of it down. This will be the trans. Okay. For cyclic compounds, the ring structure also prevents free rotation. So the cis-trans isomer of ring compounds are possible for ring structure. So you have cis and you have trans. This is receding to paper. This is coming out of the paper. Cis, trans. And also for molecules containing nitrogen-nitrogen or carbon-nitrogen double bond, also possible. You can try yourself which molecules exhibit cis-trans isomerism. Enantiomerism, the next one, refers to the existence of compounds with the same molecular and structural formula but different spatial arrangement of atoms. So a compound displays enantiomerism if it forms a non-superimposable mirror image, no plane of symmetry, and has one or more chiral carbons. Okay, we're going to talk about each of them later. So a molecule with a plane of symmetry forms a superimposable mirror image. It does not exhibit enantiomerism. These are some of the examples. Okay, they have a plane of symmetry. For chiral carbon, right, the chiral carbon is sp3 hybridized and form four different groups attached to it. A molecule containing at least one chiral carbon forms a non-superimposable mirror images, provided there's no plane of symmetry. Such chiral molecules exhibit enantiomerism. These are the examples. Four different groups. So you are supposed to mark the chiral carbon with the asterisk here. And considered lactic acid, it has one chiral carbon, no plane of symmetry. So they are mirror images which are non-superimposable. A pair of stereoisomers which are non-superimposable mirror image are called enantiomers. These two enantiomers of lactic acid are two different compounds. regardless of how you flip or rotate the molecule, right, of the lactic acid, you will never be able to obtain the structure of the molecule of the other. Yeah, that's called mirror images. It looks something like this. So you can try to, you know, rotate to this one, but it's still not the same as this one. Because it's different on the 3D. Yeah. Yeah, it's not the same. Then it will not be the same as this one. Then you rotate this. This one become on top. Also not the same as this one, right? For 3D, compare and contrast the properties of N-enantiomers. Okay, so we look at the physical properties, chemical properties, and biological properties. So physical properties, they are identical, except that they rotate the plane or plane polarized light in equal but opposite direction. Chemical properties, identical except in the interaction with another chiral molecule. Biological, different biological properties. And these are the practice that you can try yourself. Now, rotation of plane polarized light and optical activity. So for the positive lactic acid, it rotates the plane polarized light clockwise. The negative one, it rotates the same angle but anti-clockwise. If an equal proportion of each, right, it will be called a racemic mixture. So the rotating power of one enantiomer will exactly cancel the other. It will not rotate the plane of plane polarized light. So it's not optically active like this. So you have incident light vibrate all direction through the polarizer. And then one will rotate the plate of plane polarized light to the right or clockwise. The other will be anti-clockwise. How about molecules with more than one chiral center? In general, a molecule with n chiral center have a maximum of 2 to the power n stereoisomers. So for example, you have 2 chiral center, then it will be 4 stereoisomers like this. Yep. One and two are non-superimposable mirror image of one another, and they are a pair of enantiomers. 3 and 4 are non-superimposable mirror image of one another, so they are a pair of enantiomers. So 1 and 2, 3 and 4, but 1 and 3, they are stereoisomers, but they are not mirror image. So they are called distereomers. Yeah. Because they are 1 and 3, is it? Yeah, because you can actually rotate to become like this, right? Yeah, you can rotate this to become like this. It's possible. Okay. Let me see this one. A. You can rotate this to become this, yes. Okay. Meso compound is one whose molecules are superimposable on their mirror image, even though they contain chiral center. They contain a plane of symmetry and is optically inactive. Okay, so they have a plane of symmetry. So this only had 3 stereoisomers instead of 4, although they have 2 chiral carbon. Why? If you look carefully, You draw out this thing. So these are identical actually. Because, okay, why is that? They are obviously mirror image now. Okay. But X, right, and X not, they are identical. There's a plane of symmetry here. Look carefully at this one. It's the same. Plane of symmetry means it's like the two on top, right? They look similar. They are like mirror image of each other within itself, something like that. Yeah. And do yourself this one. So if I have X chiral carbon and Y double bond, the maximum number of stereoisomer is 2 to the power X plus Y. Okay, like this one. Okay, you can try yourself this. So for this one, right, it has how many? 2 chiral carbon is one here. Is it one here? One here. 2 here. No double bond between carbon, right? What? 1. So 2 plus 1. 3. Three plus 1, 4, but not cis-trans isomers. Chiral carbon, chirals at join. One, two, three, 4, 5. So 32. 2 power n, and then humors, 2 cis-trans isomers. Okay, so this is a summary. You can just read yourself this. And this one we will just keep. Okay, that's it for today. Thank you.